I'm going to be talking about dropping acid a little bit, which is a good idea with everything we've heard in the previous talk. Doing drugs always solves certain program problems. And we're also going to talk a little bit about some, well, I wouldn't call them SQL anti patterns, but we're going to talk about queries a little bit. So first, a little bit about myself. This is what I look like when I don't have to go outside in these difficult times. And if I do have to go outside, then Olaf pretends to be my smiley face. During my regular workday, I work at a company called MongoDB. I work on the PHP driver to make sure that every PHP application on this planet can connect to MongoDB if it wants to. And I also work on the C driver, which of course is used by the PHP driver itself. I'm also a member of the Doctrine organization, where I work mainly on the MongoDB ODM, but I also try to keep working on the other projects like annotations, persistence, and all of that kind of stuff that just follows the main ORM and ODM libraries. But I do try to stay away from the ORM and DBAL libraries because I'm not an SQL person, as you will find out during the course of this presentation. Last but not least, I also do a bit of work in the Symfony community by going to meetups or just lurking around in the Symfony Slack and pretending I know something when someone asks something about Doctrine. And so before we get started, this presentation is called Schema Design for E-commerce. Now, a question that I got asked a couple of times was, why e-commerce? Like, is there anything special about e-commerce that, you know, forces us to do like a nice workshop or a presentation about schema designs? So for one, data retention requirements make for some complex schemas. When you think about it, if you program an online shop, for example, you have to keep a lot of data around. You don't want your invoice to be any different because you've raised prices 2 years after the fact, right? So when someone does an order, you want to store all the product data with this order somewhere. Same with customer data and everything. That makes schemas complicated, which in turn makes it for a very good example as to how to improve things or how not to do things. The second thing is we have lots of existing examples. There are a lot of good and bad open source systems that we can look at when we talk about databases and how to handle the amounts of data that come up in e-commerce systems. So just looking at shop systems, we have Magento, Silius, Spryker, and many, many more that we can look at. Last but not least, it's catchy, right? So if I say, well, we're going to revolutionize doing databases for e-commerce applications, blah, 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 your boss is going to be like, hey, cool, I'm going to send you to this conference. If I'm going to name it, hey, how to just use MongoDB in your application, they're going to be like, not really. So yeah, this is one of the reasons why we're doing this for e-commerce. And so with all of that said, let's see how we can get started with this. So what we want to do first is we want to model our data that we want to store. Now, since we only have 40 minutes, give or take, we're not going to do it from scratch. Instead, we're going to use Silius. I don't know if some of the Silius folks are in the audience today. I saw they RSVP to the meetup, so I hope they are here. I've used Silius for 3 years, which is why I like to use it as an example, because unlike Magento or Spryker or all the other things, I actually know what I'm doing in Silius. So to get started with this, we're going to look at the product schema. And I've simplified this a little bit, but this is what we would get started with. We would create an entity relationship diagram for the data we want to store. In this case, products, for example, a t-shirt, some product options like a size for a t-shirt, some product option values like small, medium, or large. And then most importantly, product variants, which would be this t-shirt in size large, color blue, and that is our variant that combines everything. We do have some more data that we need to store along with the product, like where is it available, what's its price in a region or a channel or whatever. Do we have any attributes, categories, or whatever that we want to store? And the other important part that we want to take a look at today is the order system, which then takes a product variant and associates a bunch of data to it that is necessary when you want to buy something in a Silius store. So for example, the shipments, payment data, payment method data, your customer information, and where the packages needs to go. So all of these are connected, and we show these connections in an entity relationship diagram. And if you haven't just started doing IT, like, I don't know, in the past few years, I'm sure that you've done at least one of these in your life, especially if you've done university. And so once we've done that and we've ticked all our boxes and we figured out, okay, we have orders and payments and methods, we can create our tables. So for Cilius, this again is very easy because, and this is why I love just using something because I'm lazy, we can just copy their migrations. So what you can see is normally we do start out with pretty much the same tables that we've seen in the entity relationship diagram. We have product options, we have values, we have Cilius product, but we do have the occasional join table, in this case, to combine products and options because it's an M2N relationship. Size is an option that is valid for multiple products, and a single product can have multiple options like size and color. And so the only way we can do this in SQL is by adding join tables, of course, nothing new there. And similarly for order, we also have all these separate tables for orders, for items, and for units. We'll get to what units are in a little bit. I'll just explain this if you go along. If you do have any questions regarding this, you can either ask them directly. I hope they pop up on my screen, but I would like to just answer questions at the very end, just so we can kind of keep the flow going. So now that we have these tables, the question we have is, why don't we normalize them a little more? Why don't we just create a few more tables and say, well, we do have a product which consists of a primary key and a title. It also has a product description, which we put in a separate table. So it's ID and description. We have a product option, which has, again, a primary key and a name, and we combine products and options. And every time we want to add a new attribute or a new detail to a product, we just create a new table, because that way we never have to modify existing data, right? So, I mean, why not do it like that? What's the reason here? Or why don't we go the opposite way and say, we're going to normalize this a little less? So we're going to have our product option, obviously. We're also going to have a product, but instead of having a join table, we're just going to use an options column of type text and put in a bunch of comma separated IDs in there. So, I mean, why not do that? It might just work for a use case, right? And so to explain why we do this, I want to go back a little bit and take you all back to university or your school, wherever you learned this, and talk about database normalization and normal forms, because yay. So it all started out with unnormalized data, right? Where everybody was like, okay, well, I have this database and I'm just gonna put everything in there the way I think it, I just put it in there. So you would have, comma separated values in tables, you would have duplicated information. And at some point in time, people said, hang on, every time I have to look at that person's code and databases, I have to throw up a little bit. And it's, starting to get on my nerves. So let's just come up with a couple of ground rules that we're not going to worry about, so that we don't have to worry about this anymore. For example, let's just have atomic values. Okay, let's stop with the comma separated stuff in there. Let's just make multiple columns. And I just dropped my clicker. And so that became the first normal form that you've probably heard. And they added some, and I'm not going to list all of them. I'm not going to explain all of them. Please don't worry about that, because I hate normal forms. But the third one I'm listing because it's one of the most important ones. Because I always feel when you design a database, the third normal form is what kind of comes naturally, where you kind of realize that, well, this data belongs to this entity and in this table, and this data kind of goes over there. And the formal rule is that there are no non-transitive dependencies. In other words, to bring it with in Codd's law, is every non-key attribute must provide a fact about the key, the whole key, and nothing about the key, so help me Codd, which is a good way to remember it if you can read it off your screen, to be very honest. But this comes naturally to us. Then they added a whole bunch more over the years, and when I did some research for this presentation, I was shocked to see that it actually goes up to the sixth normal form, which is number 6, but since IT people can't count, apparently, there are 10 totals, because some of them have names, some of them have numbers. So maybe we should just refactor these someday. But the sixth normal form is what I showed in my previous example about normalizing it a little more. Essentially, it says that every row contains the primary key and at most one other attribute. So as soon as I have a table that defines a key, a name, and a description, I'm in violation of the sixth normal form. I have to normalize this. I have a table with a primary key and a name, and I have another table with a primary key and a description. And if I want both data, I need to join. It can be useful. It can be less useful. It just depends. This is very popular in data warehousing systems, not very popular in your everyday application. If you've done this yourself, I'd be glad to know what your use case was to using such a normalized database, but I've never come across a use case for this at all. So what are the pros of normalizing databases? For one, atomic columns reduce complexity. Now think about our example before where we just had a comma-separated list of options for each product. If we wanted to update that, it would be a bit of a pain in the ass to do, SQL string manipulation and just do substring to trim something out. At the same time, it's a bit dangerous to just read the data into your application, modify the memory, and then just push it back, because technically you'd have to lock the data from reading it to writing it back to make sure you're not overriding somebody else's changes. Second of all, reads can be more efficient. So if we split up long descriptions from products and we don't need the description, we don't have to read the data. In fact, we don't even have to skip over it in the database depending on how it stores our data. This can make queries a lot faster. And it's one of those optimizations that we always used to do in my previous jobs to make sure we have a constant row format in MySQL so that seeks are a lot faster. In the same way, normalizing can make your atomic updates a lot easier in that they will not conflict. As I mentioned before with atomic columns, if you were to do this, if you were to do comma-separated values in a single column, you would have to work around this problem of two processes trying to manipulate that data at the same time. Whilst if these are separate rows, we can manipulate them independently. We can delete one row and insert another one at the same time, and it will most likely not create any problems. And last but not least, when looking at the data, it can seem a lot more organized. Because if you think about having a database with a lot of columns that contain comma-separated values or serialized data even, looking at that is going to be messy. And if you're trying to find some information, you're going to have a bad day. But if you have all the data for a product in one table, well, it's very easy. You just look for one product, you look at the table, and you've got everything. On the other hand, though, we do have a few cons, and to pick up where I left off, the data can also seem a lot less organized. So if we keep normalizing our database all the way to the sixth normal form, and our product, which normally would have something like 15 to 20 columns, suddenly has 20 tables, and you need to look up some data in the database because you're debugging, well, have fun writing these SQL statements because you're going to be joining all the time. Which brings me to my next point. Queries are going to be a lot more complex because we may need to be joining stuff for left and right just to get the little bit of data that we need. We need a name, a description, we need a couple of attributes. We need to join all of that together, which makes for complex queries. Last but not least, we are going to have some added complexity because whenever we normalize, most of the time it consists of splitting up data into separate tables. So all of a sudden, our one single tiny change is going to be a change in multiple tables. Again, to beat the dead horse of the sixth normal form, if we want to create a new product, we're going to have to write data into 20 separate tables in that schema. And so we need to kind of make sure that this works. So going back to Cilius and going back to using Doctrine ORM in that case, when we create a new product, what it does is it inserts a product entity into the table. It creates the relationship between products and its options. It creates all the variants for this product. So for example, this one particular t-shirt, and it stores that this one particular t-shirt is blue in color and large in size. And so we need to store all of that. But what if the database decides that, hey, you know what? It's Saturday night, everybody's out drinking. I don't feel like doing this work right now. So I'm just gonna shut down for a moment and just relax. And in the middle of these queries, it just decides to say, well, I'm not going to write this to the database. What's going to happen? We might end up with a product in there that doesn't have any variants. That's not very good. We might end up with a product that has variants, but all of these 5 variants don't have any option values assigned. So they seem to be the same t-shirt. We don't even know what size or color they are. That is a bad thing that we need to avoid at all costs. And so this is the moment that we're just going to have some asset right now. And no, I'm not talking about this kind of asset. And unfortunately, due to the current situation, I also can't just hand out some asset to you, which I had originally planned. Wink, wink. We're going to need database asset. If you don't know what it stands for, I've got a little explanation coming up again. I don't want to bore you with too many details, but essentially these are the 4 cornerstones of transactions in databases. Atomicity, meaning that all operations will occur or none. If our database decides it wants to go out for a drink, it needs to either throw away all the queries or handle all of them, but not pick up in the middle and leave. Second of all, our database needs to be consistent. It always needs to be consistent. And if one of these operations would break database consistency, it has to be rolled back completely. Isolation, which means that no 2 transactions may modify the same data. So the database needs to lock away some data for writes while we're taking care of our one transaction. And only when we are done may another transaction modify that same record. And last but not least, durability, which is sometimes considered the most important one, which means the data is actually persisted and not lost. So if I have 4 queries and the database tells me, yep, I've done all of them, I want to make sure that they're actually going to be done, written to disk, and the next time I do the queries, I actually get my data back. And so to do this is very simple. And if using Doctrine, we don't even have to do anything. We just use start transaction and commit, and our database does all the magic. But here is a bit of a hot take, and you don't need transactions. This is something that just needs a little explaining, but you don't need transactions in your application. In fact, if you need transactions to manage your data properly, maybe you need a different schema and not transactions. So I want to give some examples about what I mean when I say you need a different schema and how we can solve these problems that we just kind of touched upon. So the first thing you need to do is stop using references. I know this is a harsh statement, but especially in e-commerce where, as I mentioned, you have data retention policies and you need to keep stuff around for later, you really don't want to use references, because let's take a look at this example. We have an online shop where a customer can create an account. So I sign up for my account and I realize, oh, there's an address book feature. This is nice. I can add my work address to have some packages sent there. I can store my home address, and I don't always have to recreate them whenever I do checkout, because that would get boring. And whenever I order something, we associate these addresses with the order. So I have a shipping address and a billing address. But what happens when I order something and I have it shipped to work, and in a few years I quit my job and I want to remove that address from my address book? Now, all of a sudden, I can't remove it anymore because we've just linked it. So I have to keep it in there. I would have to implement kind of a soft delete, which if you're using Doctrine is, yeah, there is a plugin for that, but you really don't want to do soft deletes. It's kind of an anti-pattern. So we need a different solution. As I said, if we're using Doctrine embeddables, we could just go ahead and just duplicate all the fields and put them in the table. Doctrine embeddables make it super easy because we can just mark it as embeddable and have Doctrine take care of this, taking the object, the address object with all its separate fields and splitting that up into its 5 columns and just pushing all of that in the order. But if we did that for all the data that we need to duplicate, that's going to be a lot of columns in our order table. So yeah, maybe not want to do that. Of course, we could also extract it to its own separate table, but that's just, okay, so now we create a separate order address table for this. Well, sure, but it's the same problem. We could do JSON or JSONB. This works nicely. We just create a shipping address field and we mark it as JSON, which is a little better than text and using serialized data. but we have some structure. We can query by it. So while the data is strictly speaking not atomic and violates our first normal form right away, it's also not as bad because we can actually query these addresses, or these orders in this case, by shipping country or by shipping city. We can look them up by the values in the JSON. And this works on most modern databases. So if you think about MariaDB, MySQL, PostgreSQL, all of these have JSON and JSONB types. Now, I mentioned Postgres. If we're using Postgres, we could go one step further and do something really cool and use custom types. Now, if you're using Doctrine ORM and Doctrine DBL, you're a bit out of luck here because it does not help you with this at all. But essentially, it allows you to create your own custom type that contains multiple fields. So in this example, let's create a type called address with an identifier, which might be helpful at some point in time. It contains an address field, a city, postcode, country, whatever else we want to associate with an address. And when we add this to the order table, we add a shipping address of type address and a billing address of type address. Then we can insert the data into it, which looks a little bit fancy, and you can kind of tell that SQL wasn't really meant to handle this kind of stuff. But now we have the data in our table as well. So what's the difference between this and JSON, you ask? Simple. In JSON, your database does not care about the structure at all. So while you say this is a shipping address of type JSON, it could just contain any kind of rubbish, and it does not have to be an address. Whilst in this case, PostgreSQL makes sure that you actually do have the fields that the type requires. You can even add constraints and more things as you can to all other fields as well. So this actually follows your database schema as you would have it. You can still query by it. You can still select orders by shipping country, for example. So this is one of the biggest things that you need to do if you want to start avoiding transactions, is get rid of your references. Don't pull data out into separate tables and stuff. Just keep it together. So how can we actually find out what to do and how to modify our database? So one thing that we always tell people to look at when they're designing their database is looking at your queries, which obviously doesn't work before you start writing your application and database, but it's kind of a process where you iterate over it, because your queries will tell you a lot about your potential schema issues. So let's just look at a couple of examples. What is a potential schema issue that you can see with a query? Let's say you have frequent joins. Every time you're looking for an order, you're also joining into order items and order item units to get all the data. Every time you're looking for a product, you're also joining into product options, product option values, product variants, variant values, to just figure out what are you actually going to, put in your cart, display to the user, whatever. So whenever you have frequent joins, it kind of tells you that the data belongs together. So you might want to choose a different way of storing it. The opposite is also true. If you find yourself using projections very often and only selecting a subset of fields from a table, maybe you should separate these, because when you always just select a few fields, maybe your database is getting inefficient because it stores a lot more data. Seeks are going to be slower, and it's just not as efficient as it could be. But there, as you can see, these two conflict each other. So there's always a bit of a trade-off you're going to have to make, and you're going to have to compromise on this. Another potential issue is frequent subqueries. So if you have a select from and then another select, that is just all kinds of messed up, because it tells you that, well, you need to do subselects, which are nice when you have to do big reporting stuff. But if this is in your main application logic that gets executed a whole bunch of times, maybe you want to redesign your schema, obviously. And last but not least, this is the example that we had before, frequent writes to multiple tables at once. This kind of goes hand in hand with frequent join queries, but if you do something with your data and it manipulates 5 or more tables, well, maybe it's time to start thinking. And so with this in mind, let's do an example. Let's do an actual Cilius example of what Cilius does. For example, we update the cart amount. So whenever we update the amount of items or the quantity of one item in a shopping cart, Cilius creates a new order item unit. It uses this to track shipments. So when you buy 3 of the same t-shirt and it only sends out 2, it knows it sent out these 2, and this 1 unit is still missing, being produced on the way here or whatever. It's just not in stock. So it uses order item units. It also updates the order item itself, where we say, well, we're buying this t-shirt, to say we're buying 3 of these, and the total price is going to be $19.98. And last but not least, it also updates the order itself because the price also is going up. And so it always has to do these 3 queries at once. Starts the transaction, inserts a new order item unit, updates the order item, updates the order, commits the transaction. There's already one problem we can see with this, which is isolation. We should not do this, because all of a sudden we can have race conditions in there where one set of changes gets lost. Now think of you doing this kind of change in 2 browser tabs to just mess with the developers, and instead of going up by 2, which you've increased quantity in 2 tabs, it just goes up by 1. Now this is obviously a very constructed example, but when you think about it, this happens quite a lot of times where you can lose changes. So if you want to do this properly, you'll want to isolate these changes. You insert a new item unit, you increase the quantity by a certain amount, you increase the total by a certain amount, and you increase the items total in the order by a certain amount. This already makes it a lot safer, but we haven't solved the real problem here, right? We're still doing updates in 3 tables, which, as we said, this shows we might have a little problem. And so with that in mind, let's go and do the last thing you should always do when thinking about how can I optimize the database. You look at your data. Well, we've done that before, haven't we? We've built our entity relationship diagram. We've looked at products and variants and options and option values, and we figured out, well, this is what we want to have. But for a moment, let's take a look in a bit of a different format. So instead of looking at an entity relationship diagram that already has convenient boxes for certain entities and everything, let's just maybe look at this in the way of an API response. So when you have an API that returns a shopping cart, this is the kind of data that it would return. It gives you some customer information, has a state, it has some items in there, stores the variant for an item, it stores a price, quantity, it delivers the units. So this is how we would present that data to the browser. So yeah, this is a new way of looking at it, and it's kind of nice, right? We can also make this an order. So as soon as this is an order, all of a sudden there's going to be more data, right? So it's very flexible, because all of a sudden we want to store more information about our customer. So we're also taking care of our data retention here. We've got our shipping address in there, our billing address. It's associated with the customer. It's not just referencing, so I don't need to do a separate API request. We have some payment data in there. In fact, not just one payment, but multiple ones, because it could be kind of part of a payment plan. You could have a down payment and follow-up payments. Or for example, you could just have a failed payment because your credit card is maxed out, as always in these days. And so you want to create a second payment, but not lose any details from the previous one. Same with shipments. You might have multiple shipments because items that are dispatched from separate warehouses, or some stuff is not available yet, so they're shipping out what they have and everything else is getting shipped out later. We just have multiple things and we want to store all of them in the same place, and we want to provide them to our application in the same place. So why not just store data like that? Well, when you think about it, this is a little bit difficult when using MySQL or PostgreSQL or Oracle or whatever. So we're going to use a different database, and the very familiar ones with me will know that this is going to be, of course, MongoDB. So just looking at the chat, okay. I hope there are no questions or anything. I don't see anything, so hopefully everybody's still following me and hasn't fallen asleep yet. But we're going to use MongoDB. So yeah, I don't just get paid to say this, but I've actually done this for the past, I think, 9 years, even before I worked at MongoDB. This has been my daily bread and butter. As I said, I try to stay away from doing ORM and DBEL in Doctrine because I just don't know my relational databases anymore. So with this in mind, let's start with inserting our card document. And this is exactly what we're going to do. The data that we stored before and that we presented to our application, we're going to store this exactly that way. We have an order. It consists of multiple items, each of which is an object, and each of those contains multiple units, again, which are objects and store their own data. So this works fine. When we query it, we always have all the order data. So card data or whatever it is, whatever state is in, we always have all the data. We have all the items, we have all the units. We can look up the variant by its ID, and we can handle this. So what does an update look like on this? So let's say we want to update the quantity from 2 to 3, or increase the quantity by 1 rather, in MongoDB. So this is a single query. It's a single command. It's an update command where we say, well, first of all, we want to update the item with the identifier 1, 2, 3. And the second is kind of what your set in SQL would equal, except that we have this atomic update operators. So $inc, for example, increments a field by a certain value. $push pushes a new item to a given array, or creates the array if it doesn't exist. And so what are we doing here? We increment items total by $14.99, which is the price of 1 unit. Easy. The next one is we increase the quantity of a particular item by 1, and increase the total of a particular item by $14.99, which is the price of a single unit or a single item. So how do we know which item to manipulate? Well, this is where we use the array filters that we can see at the bottom. We just define a name for this filter, in this case matching item, and we say matching item is anything where the variant equals 1381. That way we don't have to actually use array indexes, which could change if another process dropped an entire item. So we don't have to use first or last, or actually say, well, we want to update item with the index 5, because that could change. No, we just have a query, and that selects our item that we want to modify. And then we also use this to push the new unit to this item. And this does exactly that. It pushes a new unit. So we now have 3 units, and it increments all the fields. This is atomic. It modifies a single document in a single collection. It does not require any locks beyond the locking this one document. It does not require transactions or anything, and it just works out of the box. Similarly, when we finish checkout and we want to override a bunch of data, we can do the same thing. We set the checkout state to something different. We add the state, we add customer information, and we push new payments and shipments object. So as you can see, this is very different from what you've been doing most likely for the past, I don't know, 2 years, 10 years, 20 years, 30 years, however long you've been writing SQL. This is very different because it's not SQL. So I want to give a small example of how you can get a head start with Doctrine, which, being the Symfony user group, you most likely will have your experiences with, good or bad. So we have our order object, and this is always nice to see this in 2020 with type properties, even though they sometimes don't work with Doctrine. Let's be fair about that. We make it a soft final class because we still need to extend it for proxies, but we can type some things. And this is not the actual Silius order class. This is something that I just made up for this example, made it a little smaller. We have an identifier, we have a state, we store a customer, we have multiple items that we store, so we have it as in a collection, and we store a total. In our constructor, we always need to create new array collections. I just dealt with a Doctrine issue yesterday where somebody didn't, and it messed up a lot of their stuff. So pro tip, always use collections internally. And we then add some mappings for ORM. Spoiler alert, I haven't written any ORM mappings in the past 10 years, so please don't point it out to me that they are wrong. I know they most likely are. Terribly sorry about that. But we map our identifier, we map our columns, we map our references, many to one, one to many, to customers and order items. And we would do absolutely the same thing with order items and units. But we can also do this in ODM. And I'm going to go back and forth between these two slides a couple of times so you can just blink really fast and pretend nothing changes, because there aren't many changes here. In our document, yeah, we do call some things differently in MongoDB ODM. We call them documents, not entities. We call them fields, not columns. And we have this new thing where we call it embed one and embed many, which is part of the whole stop using references thing. We do have references. We'll see one in a little bit. But in this case, embed one, embed many, they take all the data and store it in our order. So this produces the example that we've seen before, where we have an array of items in our order. So this is the embed many. We also have an int field with an increment strategy. And if we take a look at this order item that we've included before, the embedded document, we have some more increment fields in there. So they're type int strategy increment. This tells MongoDB ODM that when it updates this field, it should just not set the quantity to whatever the new value is, but actually compare it to the value it read from the database whenever you fetch that document and compute the change, and then just increment it by the change value. So that even if your data was stale by, I don't know, 20 minutes because you've been doing batch processing and you've only now gotten to manipulating this order item, you've changed it from 3 to 5. So chances are you just want to increment it by 2, even if it's 5 already. Of course, this depends on what you want to do. In this case, let's assume this is the case because it fits my narrative at the moment. Again, we embed many order item units, but we also reference the product variant above. Now, this reference one is what you would have as a many to one reference, I believe. One to many, I believe, is the. I never can keep my ORM references check, but essentially we're just storing the identifier of the variant that this item is. So it's actually reversed. We store the ID of the variant in here, and we could do this with multiple ones as well. So if an order item were to consist of multiple variants, we could store multiple of these references. And to do the examples from before in reverse order, obviously this is your typical Doctrine handling. We set the checkout state to something, we set the state, add customers and shipment data, payment data, we persist it, and we flush it to the database. And it produces exactly this query where it sets some data, it pushes the new payments and shipments. That's what ODM does by default for any many or embed many and reference many objects. It uses push strategies. And so this is the exact same query that we already saw before. If we want to update the cart quantity, and in this case, Silius does a little bit of magic. With this, we say update quantity to 3. There is a quantity modifier in the background that adds a new unit for this based on the new quantity. Then we persist the order, we flush it. Technically, it would create a query like this in an ideal world, except that it doesn't do this quite yet. We are working on getting this to work because these array filters were only introduced a couple of MongoDB versions ago, and we haven't gotten to do that. So this will cause multiple queries in ODM to modify the data because it wasn't possible to do this earlier. So for every push that you do, we will actually create a separate query, but just pretend that we don't. And if you do your queries yourself through the query builder or whatever, you can just do this yourself. You don't have to rely on MongoDB ODM to do the correct thing. So this is just a small example I wanted to give how to change your schema from needing 3 tables to store your basic data to storing them in one collection and not even needing transactions for most of your business logic. So when you think about it, one document, we don't need to lock any other tables. We don't need to lock any other rows. We just have to lock our own one document in the collection. Our isolation is given because we're doing the whole $inc stuff. And our durability, well, MongoDB is taking care of that using write concerns that I don't want to go into here because it would just go into far too much detail. But I'm hoping that this gave you a little bit of an insight into what we can do to get out of these old patterns that we've been doing for the last whatever many years we've been doing this, with splitting data up to just fit some artificial narrative about what our database is supposed to look like. So maybe next time you design your database, think outside the box a little bit, think in different patterns, or as I always like to make a bad pun, think outside the table. And with that, this is my last slide. I would like to say thanks for sticking with me and listening to me droning on about MongoDB.